All right, today we are diving into a really powerful tool that data scientists absolutely love. It's called Principal Component Analysis, or PCA for short. And honestly, it's the secret sauce behind everything from facial recognition to predicting the stock market. So, what's the magic here? Let's get into it.
So let me ask you a question. What could facial recognition and, say, trying to predict the economy possibly have in common? I mean, on the surface, they seem like they're from completely different worlds, right? But they both share one massive fundamental challenge. They are drowning in data. And it turns out the key to making sense of it all is the exact same technique. Just think about it for a second. A single human face in a photo is made up of thousands upon thousands of pixels. Each one is a tiny little data point. A financial model, it might be tracking thousands of different economic indicators all at once. When you've got that much information with all these tangled, complex relationships, seeing the real underlying patterns is, well, it's pretty much impossible for a human. And that's exactly where PCA comes in. It helps us slice through all that noise and find the actual story the data is trying to tell us. And this gets us right to the heart of the problem PCA was built to solve, something called high-dimensional data. Now that sounds super technical and intimidating, but it's really just a fancy way of saying you have way too many variables or dimensions to wrap your head around. Take the world of genetics, for example. A scientist might have samples from, say, 100 patients. But for each one of those patients, they're looking at maybe 40,000 different gene expressions. Trying to find the one or two genes linked to a disease in that mountain of data, it's not like finding a needle in a haystack. It's like trying to find a specific needle in a giant mountain range made entirely of other needles. You'd be completely lost without a way to simplify things. So how in the world do you deal with that? Well, this is where PCA comes in with just a really elegant and beautiful idea. Instead of just throwing data away, which feels wrong, we're going to find a much smarter way to look at it. Imagine your data is just this big, messy cloud of points floating in space. The way we're looking at it now with our thousands of different variables isn't helping us see the actual shape of that cloud. What PCA does is it essentially rotates our perspective. It gives us a brand new set of axes that are perfectly lined up with the most important patterns in the data itself. And these new axes, these are what we call the principal components. Each one is a clever combination of all your original variables, specifically designed to capture as much of the data's story, or its variance, as possible. So the first principal component, PC1, grabs the biggest, most important piece of the story. Then PC2 comes along and grabs the next biggest piece that's left, and so on, until we've squeezed out all the important information. Okay, this is my absolute favorite way to think about it. Imagine that data cloud is floating in a completely dark room. PCA is like finding the one single perfect angle to shine a flashlight on it so that the shadow it casts on the wall is as wide and as spread out as it can possibly be. That shadow, that is your new simplified view of the data. It's a lower dimensional projection that has preserved the most important information, the most variance. It's just brilliant. So we get the why. We want to find that perfect shadow. But how does it actually find that perfect angle? Now, while the math behind it can get a little hairy, the basic recipe is actually pretty straightforward. Let's take a quick look. Okay, so first, PCA looks at how all of your variables move together. Do they go up at the same time, or does one go up and the other goes down? This is all captured in something called a covariance matrix. Then, through some really clever linear algebra, it finds the key directions of variation in that matrix, and these are called eigenvectors and eigenvalues. Finally, it uses those to build our new axes and redraw the data from this brand new, much more insightful perspective. And those two terms, they're really the whole game. In our flashlight analogy, the eigenvectors, they tell you which direction to point the flashlight. They define the angle of our new principal component axes. And the eigenvalues, they tell you how good that direction is. They measure the size, the magnitude of the shadow. A huge eigenvalue means that that axis, that component, is capturing a massive amount of the data spread. So what does this all actually look like when you do it? This is the fun part. This is where the magic really happens, and you finally get that aha moment where the hidden patterns just pop out. So here we go. Here is our data before PCA. It's a bit of a blob, right? You can kind of see a vague diagonal trends happening, but it's messy. Those dotted lines, those are the new axes that PCA has calculated as the absolute best way to view this data. And notice how one of them slices right through the main direction of that data cloud, perfectly lining up with that chart. And boom, here's the aftershot. The entire graph has been rotated to line up with those new axes. Now, the main spread, the biggest variation in the data, lies perfectly along the horizontal axis. That's our PC1. And the vertical axis, PC2, is just capturing the little bit of variation away from that main trend. The pattern that was hiding in there is now perfectly, beautifully clear. It's awesome. And here's what the results look like when you see them in a table. This shows us how much of the original data story each of our new principal components is telling. Check out PC1. It captures over 44% of the total variation all by itself. That one new variable explains almost half of everything that's going on. And look at the cumulative column. By the time we get to PC3, we've explained over 84% of the entire story with just 3 new variables, instead of the original, say, 8 or 10. That is a massive simplification. This leads to a really practical question, right? How many of these new components do you actually need to keep? Well, there are 2 common rules of thumb. The first is called the Kaiser criterion, which just says keep any component that has an eigenvalue bigger than 1. Or you can just set a goal for yourself, like I want to explain at least 80% of the variance, and you just keep adding components until you hit that target. Now here's the crucial point. These new components aren't just some abstract math. You can actually interpret them and give them meaningful names. By looking at which of your original variables have the biggest influence, we call these loadings. You can figure out what the component represents. So in a financial dataset, maybe PC1 is a combination of things like age, savings, and job stability. We could call that component financial stability. And maybe PC2 is mostly about debt and payment history, so we could call that credit history.
Okay, let's zoom out. We've seen the what and the how. But why does this all matter? Where is this technique actually being used out there in the real world to make a difference? The answer is pretty much everywhere. In bioinformatics, it's finding those critical genetic markers we talked about. In finance, it's building better models to predict market trends. It's even used in image compression. You know, the tech that lets you send a photo on your phone without it taking forever? That works by reducing the image data down to its principal components. PCA is truly one of the great workhorses of modern data science. Now, one last thing. You'll often hear PCA mentioned in the same breath as something called factor analysis. They seem similar, but there is a really key difference. PCA just takes your existing data and finds the best way to summarize it. Factor analysis tries to go a step further. It tries to model a hidden, unobserved factor that it thinks is causing the patterns you see. So you can think of it like this. PCA describes what is there, while factor analysis tries to explain why it's there. And that really brings us to the final, coolest thought about all of this. The true magic of PCA is that it doesn't invent anything. It doesn't create new information. It just gives us that new perspective, that perfect flashlight angle that lets us finally see the structure that was hiding in our data all along. And it really makes you wonder, with the insane amounts of data being generated every single second of every day, what other profound hidden patterns are out there, just waiting for us to shine the right light on them?